All right. But I've only got one recording for this class because you guys are in the concrete class. So hopefully I don't screw this up. Anyway, so week 4, right? We're going to talk about a few things today. We're going to talk about steel bar. So I think there was a steel bar that was passed around earlier. So hopefully you got a feel of, it was an N16 bar, which just refers to the diameter. So it's 16 millimeters diameter, I guess. And then you got a feel of how heavy the steel was and its like density and stuff like that. So keeping that in mind and having like a physical idea of how heavy the rebar is will give you more empathy towards like essentially steel fixers and stuff like that. Because if you spec really, really heavy concrete, they're going to be very, I mean, not heavy concrete, heavy steel, they're going to be very annoyed. Okay. So, yeah, we're going to talk about steel first. And then we're going to talk about durability design, which is basically to do with chlorides and to do with fire protection. All right, I'm going to raise this a little bit. Okay, and then we're going to talk about load combinations and a little revision of statics. So yeah, basically it won't be too difficult if you've done steel structures in term 1, but if you didn't do steel structures, then I'll basically explain it from scratch, so don't feel like you're behind. Okay, so let's talk about where we're up to in the course, right? So we're up to week 4 now, and we're finally getting into reinforced concrete design. Okay, so now we're talking about how does the steel, which sits inside the concrete, combine and give structural properties to the concrete, okay? Yeah, so largely the topic for today is about steel, okay? So let's start with the steel properties, okay? So I kind of covered some concrete properties last week, right? You know, things like concrete's very economical, right? We use a large amount of concrete, but it doesn't cost that much per ton. And it's got decent strength in compression and things like that. So in contrast, steel is very, very strong, right, compared to concrete. It's got a high yield strength, which if you've done steel structures, you'll remember the yield strength in that course was denoted by F referring to strength, and then Y referring to like its yield limit. But in this course, we call it FSY, okay? So it's a little bit different because we're working with multiple materials, okay? So you basically need the S in order to specify this is about the steel and not the concrete, okay? It's very stiff in terms of elastic modulus, right? So in terms of that stress strain curve, you've got, say this is like a material curve for steel. You've got a very high gradient in the elastic region, right? Which allows it to be very stiff is the way that we describe it. The other thing about steel is very dense, it's very heavy. Okay, so this symbol here is rho, rho S referring to the density. So it would be 7,850 kilograms per cubic meter. Okay. Oh, the reason I did a cross here is like, that's just kind of saying like this is a disadvantage in a lot of ways, right? The fact that steel is very heavy. And then, but like conversely, a tick would refer to it being like a very beneficial part of, like it's like a con. Sorry, it's not a con. It's a pro in terms of the material properties. Okay, so the next one I'd like to talk to you about is the fact that steel is very ductile and it's very reliable. It's very ductile in the fact that when you, so imagine this is the steel reinforcing bar, right? If you stretch it, right, in tension, you'll see this like plastic necking effect called, and we can measure the elongation before it ultimately fails in fast fracture. So the fact that it has this stretching behavior tells us that it's ductile, right? And the other thing is the fact that it's reliable, okay? So if you remember, and okay, if you did, actually no, am I explaining too far ahead? Okay, I won't explain the capacity reduction factor yet. Okay, it's very reliable. So what do I mean by reliable? I'm talking about the material properties are very consistent from bar to bar. Okay, so if I've got one reinforcing bar and it's like visually identical to another one, you can imagine that they will both behave very similarly, as opposed to, let's say, two concrete cylinders, right, in compression. Because of the microscopic fractures in the concrete cylinders, they're less reliable than the steel, okay? The steel behaves more consistently. So that's what we are saying when we say reliable, okay? The other advantage of steel reinforcement is that it's mass produced and is also easily distributed in standard sizes. So like the bar that I passed along earlier, that's an N16 bar. So it comes in the standard size in terms of its cross-sectional diameter. Yeah, and it's mass produced, so it's easily, I guess, like it's standardized across Australia. So whether you're in like WA or Queensland, you can expect to get the same kind of steel product. Okay. Yeah, the problem with steel, or one of the problems, is that it's rather expensive. So you measure it per ton or per kilogram, right? The cost per amount of weight, right? That's how they would measure it. And then in terms of carbon emissions, right? So CO2 emissions embodied in the steel, like during its overall like production process, is rather intensive as well per kilogram. As I mentioned last week, we use concrete, we use up concrete the most out of any material other than water in the world by volume, but per ton, it doesn't cost as much CO2 as steel. Okay, so we use less steel, but the steel has more embodied carbon. Okay. Okay. Now the problem with steel is that you also need good, like a good sense of durability design in order to avoid primarily two like durability issues. Okay. The first one is the fact that steel can melt and is sensitive to high temperatures during fire events, right? So if a building's burning down, you can imagine you have to protect the steel from melting and losing a lot of its structural capacity. And the other one's pitting corrosion, which I mentioned, I believe, last week a little bit, in terms of the fact that the steel can rust. And when it rusts initially, it forms this kind of brown rust protective barrier. But once that protective barrier has been breached, this process known as pitting corrosion happens, which starts to wear away at the cross-section of the steel, and you get a lot of durability, a lot of strength issues at that point. Okay, so that's pretty much all I had to say about steel. One more thing that I'll point out, right, in case you haven't seen this before, is on a material curve, steel behaves very similarly in tension and compression, okay? Just because of the metallic lattice structure of its atoms, whether you're applying tension or compression on steel, it will behave very similarly and also have the same yield strength, whether you're referring to the tension or compression, okay? Do you guys have any questions so far about what I've been yapping about? Or not so much, okay. So I just got paranoid that I'm not recording. Okay, no, wait, we are recording, all right. And also paranoid I'm on the wrong document. Okay, no, we're good. All right, so material properties of steel, I'll give you some typical values, right? So the first one is the yield strength of the steel we consider as 500 MPa. Okay, so this is a little bit different to what you saw if you did steel structures last term, because steel structures referred to like I-shaped beams and, you know, rectangular hollow sections and things like that, where the yield strength of the steel was more in the ballpark of about 300 MPa. Okay, so here's what we refer to as mild steel. Okay, mild refers to the carbon content in the steel alloy. So remember that steel is an alloy of carbon and iron, right? So the proportion of carbon in the steel alloy determines whether it's, you know, mild or high carbon content steel, etc. So as you increase the carbon content in the steel, it becomes stronger but more brittle. Okay, that's a kind of a trade-off. This is a very like simplified version of the metallurgy right behind, I guess, like steel. But my point is, the steel reinforcement is not mild steel. It's actually got a higher carbon content than what you would see in structural steel, okay? So structural steel is the one with lower carbon content. Reinforcing steel for concrete is higher carbon content, okay? Does that make sense? Okay. But you'll see the same elastic modulus as we saw back in steel structures. So 200,000 MPa is a pretty typical number. Okay, the strain yielding limit of steel. If you think about the formula for elastic modulus, right, you're thinking about the slope in the material curve, right, the rise over run of stress over strain. If you rearrange this equation for strain, essentially you get this, right? You get stress over elastic modulus. This is essentially how you can deduce the strain yielding limit, right? So you get the strength and yielding of the steel and divide it by the stiffness, okay? We'll get back to what this means next week when we start to do calculations regarding strain, okay? And the other one is basically the breaking point of the bars in terms of how much strain or how much stretching the bar undergoes before it snaps. Okay, so this is a measure of ductility. How much elongation the bar can take before it breaks is a measure of how ductile it is. Okay. Okay. So in terms of bar types, right, there's a few kind of perspectives we can look at bars from. The first one is through its shape. So the bar that I passed around earlier in the workshop was a deformed reinforcement bar, which is just to say that they have these ribs on them, okay? And this is pretty standard, and I'll explain why we use deformed bars primarily in reinforced concrete. Once I explain what bond and stuff like that means, okay? Which will be in a few minutes. As opposed to this, sometimes you see plain reinforcing bars like so, and this is where basically the bond isn't as important, right? You might spec round bars, but to be honest, when I was working in industry, I never spec'd round bars. I always spec'd deformed bars, but there are instances where there are marginal benefits for having plain reinforcement without the deformed ribs, okay? Oh, sorry, another note that I've got here is that the most commonly used type of steel product is D500N. D refers to deformed, the shape. 500 refers to the yield strength. So as I mentioned before, 500 MPa reinforcement is pretty standard. And then N refers to the ductility. Okay, so normal class ductility, it gives you 5% elongation, okay, as a guaranteed amount of ductility. Yeah, just talking about the yield strength, other values you might see maybe pop up in this course is 250 MPa. So that's if it's like a lower yield strength steel, maybe a more mild steel or something. And you've also got 600 MPa steel, which I'll talk about briefly as well in a bit. In terms of ductility, a low amount of ductility would be 1.5% elongation. Normal reinforcement should satisfy 5% elongation, okay? And then for earthquake levels of ductility, it's kind of funny because there's a bit of contradiction, I realized. In AS3600, which is the standard that we use for concrete structures in Australia, it says 5% ductility as well, also 5% 5% elongation, for earthquake bars. But in this standard, which is for Australia and New Zealand, this is like the steel bar, kind of manufacturer's standard that they have to abide by. It says that earthquake bars should have 10% ductility, not 5. So anyway, I thought that was interesting. Okay, CEN 600, and for my PhD project that I'm researching, this is actually an industry sponsor of what I'm doing. So I don't know if there's like a conflict of interest, like telling you guys about this, but it is an emerging technology that you should probably know about if you want to be a structural engineer, because I believe that in the near future, you will start to see this bar product pop up. I'll pass this around probably in like the, actually no, I might pass it around now. Sorry, I'll come around. It's like a little pamphlet basically. Just, you can slowly have a read of it, no rushing like passing it around, just read as much as you like. But essentially, CVEN 600 is a 600 MPa yield strength bar, okay? And so it's higher strength, but if you imagine, for example, you've got a 500 MPa normal ductility bar, okay? And let's just say it's the one that I passed around before. It's an N16, okay? So the diameter is 16. The idea of the CVEN 600 bars is that they have a smaller diameter, right? But since they have a higher strength of 600 MPa, they have equivalent force capacity, okay? So if I look at this table, for example, you've got your 500 MPa bars, and if you're looking at N16s with 16 mil diameter, the equivalent would be an S15, right, which actually has a 14.6 mil diameter. And if you think about the equation, like that force is equal to, well, firstly, axial stress is equal to force over area, right? So if I rearrange this for F, the stress multiplied by the area, right, is the formula for the force, right? So the idea is that you've got the same amount of force because you've got a higher stress, so you reduce the area to match, okay? So that's essentially how this works, right? There's more to it than that, but you will probably see this starting to pop up in the next few years. Okay. And the little pamphlet thing that I'm passing around is just a brochure telling you more about it. But probably the one thing to keep in mind is the fact that since you're using smaller diameter bars, one, they're lighter, and two, they use less steel. So there's some carbon savings in that as well. All right, any questions regarding that? Yes?
So they use less steel and they're lighter.
Mm-hmm.
So what's like the parameter that makes them stronger?
The yield strength. So overall, let's say we want an equivalent force. So let's just say for whatever reason, I'm just going to make this round numbers. You've got, actually I'll do it in newtons, okay? So you've got 100 newtons of force that you want to carry through your reinforcement. Let's say that for a 500 MPa bar, okay, you know what? I'm going to make these numbers easy for myself. Say I want 500 newtons of force going through the bar, okay? For 500 MPa steel, okay, and these are just made up numbers, right? You would need 1 millimeter squared of area, right? This is just made up numbers. If I want the same amount of newtons going through it, right, and I've got 600 MPa bars, right, you can imagine that this number is less than 1 mil. See what I'm saying? So you reduce the area, but the strength of the steel is higher. Yeah.
So I meant like what the physical property is, like how come?
That's actually a good question, and I'm not actually looking at that myself because it's to do with the material science and the metallurgy. They changed the chemical composition. It's some kind of like brand formula that they came up with essentially. But if you look at the standard, like if you're interested, basically, you can look at this standard. Okay, that's the steel bar manufacturing standard, and it will give you a good idea of for the 500 MPa bars, what the chemical composition is of the metal bars, right? And then you can see that they basically tweak the ratios in order to get the highest strength output. And the idea is that they also have normal ductility as well. So they didn't want to trade off how ductile it is. They figured out some kind of chemical formula, right, which keeps it at the same ductility but increases the strength. This is like their brand secret or whatever. I don't know exactly what it is. I just test the bars. Okay. Do you guys have any other questions about that? Yes.
Is it cheaper? Or
It's more expensive. So there you go. That's why. Yeah. But it looks better for because you're doing all these like carbon saving things, right? And so in terms of like from trying to sell it to an architect, right? There's something called the Green Star rating for buildings. You can get more green stars by using more sustainable products, as such. Yep.
so is the idea of this as well if we decrease diameter, we get thinner slabs because we can have less cover between our
Okay, that's a good question. The short answer, and I can tell you the long answer later. The short answer is we don't use it for slabs. Okay, we actually use it when strength governs. Okay, and the applications that I have in mind is more so columns, which you'll learn about in week 10, piles, which you don't learn about in this course, unfortunately. But the short answer is when strength governs, it is actually, there's an inflection point and this becomes the more viable product. But for slabs, you learn about it a little bit in this course in week 9. But for slabs, it's actually deflection governed. That structural element is deflection governed. It's not strength governed. So it's not a good idea to use this product. This isn't like a magical product that solves every problem. Yeah, it's not a good idea to use this product for slabs. Okay. Any other questions? Yeah, we'll move on. Okay, sorry, that's a random ad placement in my class. All right, so bar sizing. Okay, so there's going to be this table that you're going to refer to a lot, which tells you, like, say you're dealing with N16 bars in your design. It tells you something called the nominal area, okay? So the nominal area is essentially just the actual area, but rounded to the nearest 10 mil, okay? So you might be wondering, why would I want a less accurate number and like use the less accurate number rather than the more accurate number in my design? And also, in some instances, it's actually less conservative, right? So the more accurate number would be 616 for your calculated bar area. But you're actually rounding up in this case, which is kind of a no-no in general for design. But I'll kind of tell you why. The first reason, and this is a bit of a stupid reason, is it's industry standard. Okay. So in other words, this is the way that we've always done it, so we're going to keep doing it like this, okay? Which is not a good reason. I don't agree with it, but that's one, okay? So you're like, since you guys are students, right? Yeah, we're trying to teach you stuff which is going to apply in the future when you're in an industry role, right? The second reason is the accuracy error is not significant. Accuracy error small. Okay, so let me tell you about a very quick example, and I'll get into this more when I talk about load combinations, right? But imagine you're designing scaffolding, okay? And you may not have heard me talk about this before. You're designing scaffolding, and you're interested in designing the strength of this steel structure or whatever. You've got, say, 3 tradies on it, okay? And each of these tradies weighs 100 kilos, okay, just for the sake of argument. Now, you wouldn't design this structure to hold exactly 300 kilos, okay, of weight, because that's dangerous, right? What if one of the dudes jumps? Or what if a bolt isn't installed properly or something like that? So there's this idea of a factor of safety, right, which you may or may not have run into before in your engineering degree. This idea of factor of safety is that for anything that imposes a force on your structure, you might want to exaggerate it, okay? Just for example, you might want to exaggerate it so and pretend that it's a bigger force than it actually is, okay? And for your structure, because there could be missing bolts or something, you might want to reduce its capacity to some amount as well, right? So this kind of logic is called conservative design. Another word for it is called over-engineering. Okay, so why do I bring this up? Well, it's because when you think about rounding to the nearest 10 mil, you're not really over engineering, and you're not really under engineering either. All right, this is rounded. There's a bit of an accuracy error. Where there's this kind of conservative design comes later. Okay, so when I tell you guys about capacity reduction factors and stuff, you'll see that this kind of conservative thinking is applied at the end. Okay, so for now, this is just a minor accuracy error. Okay, all right. So that's basically the justification on why we use nominal area in bar sizing. Okay, as I briefly mentioned before, the density of steel is 7,850 kilograms per meter cubed, right? But as you can see with the bar that was deformed, so this is the cross section of maybe the bar that you've seen while I was passing it around. It's not a perfect circle, right? You've got these, you might have a bit of an oval shape, you might have these transverse ribs or longitudinal ribs on it and stuff like that, right? When we say nominal diameter, we're referring to as if it was a circle, okay? So the way that you basically figure that out is like you get the calculated area if it was a circle, right? Which is just a matter of plugging in the nominal bar diameter of 16 mil, right, into this equation. That gives you, I've called it AO. And you want the linear mass, right? So you want to figure out how heavy this complicated shape is, right, per meter, by pretending it's like a circle, okay? And then you get 1.58 kilograms per meter, which refers to this number if we took N16 as an example. Okay, does that make sense so far? All right. Now I'm going to talk about a few things which aren't in this course, but just bear with me, okay? They're important. Okay, so for steel, okay, say you want to resist the effects of salt or like chloride ions, right? So you don't want these steel bars to rust, okay? Now, the best option for you is to increase the concrete cover, okay? So what do I mean by that? If this is my concrete, okay, and then this is like a beam cross section or whatever, okay, I've got longitudinal bars which run in and out of the page, and I've also got transverse bars, which I'll get into that in a bit. Okay, so it might look like that. What I'll tell you about later is this idea of cover, okay, C. So you might want to increase the thickness of the concrete surrounding the bar or move the bars further in order to basically protect the steel from rusting. That's the best way, because you don't need any new material. You don't need to introduce any like new material, basically, right? However, for specific scenarios where there's a high chance of corrosion or you know, like attack from salt water or something, for example, you might want to consider using special materials, right, or coatings. Okay, so the term black bars, which just refers to uncoated bars, right? And it's usually used in the context of how you want to treat the bars relative to black bars, right? So you've got black bars, and then you might want to do a few things, right? So two of these are applied after the fact. Stainless steel is a part of the manufacturing process, okay? Of the bars themselves. Okay, so what are they? The first one's fusion bonded epoxy, right? FBE bars, all right? Now these look really yummy because they're like green and they look like candy or something. You can call them green bars if you like. The idea is that you have your bar, right? That is just your black bar, and you sandblast it, right? So you grit blast it so that it has this kind of rough texture when you're touching it. Okay, so you've grit blasted it, and then you spray it with epoxy, right? And it's called fusion bonded. So when it sticks on, it stays on. Okay, it acts as a physical barrier for the chloride, so that it doesn't end up touching the black bars. Okay, the next one is hot dipped gal bars. So the idea of hot dipped gal bars is, yeah, you've got your steel reinforcement, and then you've got this hot vat of molten zinc or zinc-rich material, and you dunk it in. And when you lift it back out, what happens is that there's like a crystal lattice of galvanizing that forms over your bar. And I guess one advantage of this, it's easier to see. It's easier to see if I was talking about this in the context of like an I-beam, right? So if I dunked an I-beam in there, right? Same concept. Oops. Yeah, anyway, just pretend I did the little animation where it dunks in and out. The cross-section of this mild steel beam looks like so. And what's really interesting is if I zoom into here, for example, right, the top flange, like so, the galvanized layer has a very uniform thickness, like so. Okay, so literally the crystals form so it has a consistent thickness around these like kind of sharp bends, right, which is pretty cool. Why is that different to the first method that I was telling you about, the fusion bonded epoxy? Let's do green because it's fusion bonded epoxy. Because if you grit, blast, and then stick on with epoxy, what happens is around corners, you get kind of like a thinner, you get a more beveled edge, I guess. So it doesn't stick as well to corners. All right, so that's one problem with it. Anyway, why am I talking about this? Okay, so hot dipped galvanized bars is very common for if we want additional corrosion protection. The last one is stainless steel bars. Okay, so stainless steel bars, instead of using zinc like galv bars, right? We use chromium, which I think is Cr, I think. Except this actually changes the steel alloy itself during manufacturing. So instead of making the steel reinforcement and then doing stuff to it, this is part of the liquid metal alloy mix, right? You infuse it with chromium, okay? And it gives you stainless steel bars. Okay, so let's look at the pros and cons. Sorry, so I did mention fusion bonded epoxy already. It acts as a physical barrier. Hot dip galv bars act as a sacrificial anode, right? Which just means that the zinc will take on any of the chlorides rather than the steel itself. Stainless steel bars are just essentially corrosion resistant to begin with inherently, okay? So they have a high chloride tolerance. In terms of damage, the problem with fusion bonded epoxy is that that protective layer can actually get chipped very easily, okay? And also it needs to be UV protected, so you can't leave this out in the sun. Hot dip gal is quite good with self-healing, right? So the galvanized protective layer actually self-heals over time. And also is patchable with paint. So if you have a zinc-rich paint, you can also coat over areas that have been kind of bruised on site more easily. And then stainless steel is also self-healing, and it's easily the best in terms of corrosion protection, but I'll tell you why it's a problem, okay? So you've got black bars, right? And essentially fusion bonded epoxy is the cheapest option, but it still costs you essentially 30% on top of whatever you'd pay for the black bars. Galvanized bars cost you about 40% on top of what you would pay for black bars, but stainless steel costs around 6 to sometimes 8 times as much as the black bars. So you would only use this in very like extreme scenarios, like for example, if you were pouring like an underwater bridge pier or something, right? So if you've got a bridge that goes over like an ocean or something like that, and you're pouring the piers for it, you might consider stainless steel. And then bond strength. So I'll talk about bond strength in a second, but essentially galvanized bars and stainless steel don't really affect the bond strength, but it is weakened if you use fusion bonded epoxy. Essentially, fusion bonded epoxy is slipperier than the other types, okay? All right, so let's talk about bond strength, okay? Listen, this is not formally in the course either. It's actually in advanced concrete. However, the reason I'm telling you about this is it's gonna play into the first question, okay? So just bear with me, all right? This is also something that I wish I knew, like when I was taking concrete. It's a very short topic, so yeah, I don't understand why they don't teach it. Anyway, so I'm not going to tell you actually how to do the maths. I'm going to tell you the theory. Okay. So has anyone here done geotech last term? Can you just chuck your hand up quickly if you've done geotech? Just give me an idea of. Okay, about half the class, maybe a bit less. Okay. So. Okay. I'll explain a bit more then. Okay, this might remind you of piles, right? If you've done geotech last time, that's what I'm trying to say. Okay, so if you think about the equation, force is equal to other way around. Sorry. So stress is equal to force over area, except we do the shear version, right? So shear strength or shear stress is equal to shear force over shear area. Okay, we're looking at this essentially, right? So the idea is that if you have some kind of force that's applied that causes shear, if you divide that by your shear area, you get how much stress is being experienced. Okay, so when I say shear area, I'm referring to essentially the cylinder's area that's not the circle parts. Okay, so the outer shell part of the cylinder. Okay, so that follows this formula. So the circumference of a circle multiplied by the length, right, of that cylinder. That's essentially what bond strength is. Okay, actually, sorry, a bit more context. So if I've got a concrete beam, okay, and let's say I draw in the tensile reinforcement like so. As this beam bends, all right, oops. As this beam bends like so, using engineer's beam theory, we want to say that the top side is in compression and the bottom side is in tension, right? However, we've basically assumed something that I haven't explicitly stated. We've assumed that the concrete and the steel can essentially shift perfectly in line with each other, right? So this is a composite material, right? Reinforced concrete is a composite material. It has two materials, right? It has concrete and steel. And for them to basically move together as a beam is bending, we say that there needs to be enough bond strength, okay? So essentially, there needs to be enough bond strength to hold these two materials together as your beam or whatever is experiencing bending. Okay, so that's why it's important to have enough bond. So if we rearrange for L, right, it might seem a bit random for now, but I'll explain why. If we rearrange this equation for L, we get this rearranged version of it, okay? And this is called the bonded length, and this takes form in two ways, right? You get the development length and the splice and lap length. So these concepts, at least to me, were not immediately obvious why we do it, but first I'm going to explain the splice length and then I'll explain the development length, okay? So a splice length, if you imagine two planks of timber, okay, so we've got one like so and one like so, okay, and they're being pulled apart, but they're being held together with a glue surface like so, okay? So you've got these two bits of wood and they're shearing apart essentially, okay? So we know that, you know, this timber might have some kind of cross-sectional area and we've got some force applied to it, and it's also got some kind of inherent strength, right? So the strength of the timber or whatever. So we actually, like, say we don't want to tamper with any of these parameters. We don't want to tamper with how much force it carries. We don't want to increase the cross-sectional area of our timber, and we just can't modify the strength of the timber itself, right? But what we want to ensure is that these two boards don't come apart, right? This glue joint doesn't come apart. So what can we change in order to guarantee, like say this is currently slipping and breaking, what can we change in order to guarantee that this glue joint doesn't come apart? Yeah. Okay, that's a good point. This is something I didn't mention. Let's say that the glue has a certain strength as well that we just can't change. Yep.
The lap distance.
Exactly. That's exactly what I was looking for. So if you lap these more, you can guarantee that the glue joint doesn't come apart, right? And we haven't changed the cross-section of the timber or anything like that, all right? So this is what we kind of call a secondary design consideration, right? You can modify how much you lap by. So going back to reinforced concrete and why we have to calculate the lap length between two bars, right? So you've got these two bars, and in order to ensure that they don't come apart when the beam bends, you can lap them more, right? You can increase this lap distance here, okay? Does that make sense? So this is the whole idea of bond and increasing your lap to increase the amount of bond capacity that you've got. A very similar thing happens with development length, except, let me just show you a quick picture. Boat anchor. Right. How does an anchor work? Okay, so you've got a boat, right? Let's say you've got a boat and there's wind is blowing the boat to the right. We've dropped an anchor into the ground, right? So it stops it from moving. Okay, so why do I bring that up? Just let me cook real quick. The idea of a development length is that you're developing enough anchorage, is what it's called, to the concrete, right? By having enough development length. So this is essentially where you've just got the one bar, right? Whereas before we were talking about two bars being overlapped. You've got the one bar, but we still need enough bonded length in order to anchor the steel into the concrete, okay? Okay, lastly, hooks and cogs for tension development. So the idea is, you may have seen these before. This is called a hook and this is called a cog, okay? And the idea is that the Australian standards will tell you you're allowed to halve the development length in tension if you put one of these details at the end of a tension bar, okay? So in other words, if you did this, you can essentially half your development length. Does that make sense? All right. So it acts as a better anchor because it has this kind of additional mechanical interlock that engages this entire part of the concrete, okay? All right. One more thing before I do the first question. Placement of a Rio in a beam, of Rio in a beam, okay? So if you think about positive and negative bending, so like I drew a second ago, right? So if you've got a beam in bending like so, and there's gravity loads pushing down on it, the tension side will be the bottom and the compression side will be the top. So I want you to think about the compressive reinforcement. The reason we add tensile reinforcement, particularly to concrete, is because its compression strength is actually already good, but it's particularly weak in tension. So we want to place the bars on the tensile side, okay? So for positive bending, which is also called sagging moment, you're placing the tensile steel on the side with tension, essentially, and that's the case for negative bending as well. So if the beam bent this way, the tensile side becomes the top side, and that's where you would place the reinforcement, okay? So what I'm going to do is, and I'll give you guys a break soon, but I'm going to give you guys a printout of the first question. I want you to give it a crack yourself for different scenarios, right, of where the tensile reinforcement should be placed. So I'll hand that around in a second, and yeah, you can do it by yourself, or you can do it in pairs or whatever, doesn't really matter. Okay. Here we go. Shall I do it by myself or yeah, sure. I'll give you guys 3 minutes. Do that. Yes, you guys want to do it together or pairs? Just throw away the tensile stuff. You guys want to do it as save me for time. Just give that a go, yeah.
No, that's okay. No, that's okay.
Yes, but you don't want yours still be curvy. You want them to be straight.
I can actually relate to that.
So, I just want you to draw where the tensile
And it's like,
before I can't believe between that tensile. That's a big one. Yeah. Shear force and like similar reaction. So shear force is going to jump up. Jump up. Your point moment is going to cause it to lose light.
I like the honest way. So like,
It might not immediately be obvious, but you know why I'm implementing my so I've done it, I've drawn it. So we haven't taken every kind of scene. We flip it because this actually tells you the tension side. So what that means is since this is above the line, the tie cancels my point is that's exactly the way one of the ways you can think about it is into your reflection. So if you push down on it,
oh, because it's like, so like,
it's like being stretched. I'll let you do that. Because we do it like 10 minutes. Actually, see if you're But this is how it goes in terms of the reflection and the structure itself. So you notice why this that's the hardest one. Well, you've already why is this such So I'll Oh, no, fair enough. So the green lines. That one makes me
Okay, so that's fine. And then you said I'm not sure. I
Yeah,
some of the times, how are you like? Janet doesn't have fruits.
very close. Leave it like that for now. Try to wins and
Well, they can, but it doesn't sound when I dropped it, it counted as a substitute, but then online, it doesn't show up.
But you don't actually use
Yeah, exactly.
He talks about so much.
Definitely, mate. The tensile stress is a function of like so then you have a diagram of that on top. So the middle part is serious tension, which means large that. And then
I'm sure. You had
Alright guys, look, I don't want to run too over, so I'm gonna run through the answers for this question. I'll give you a very short break. Yeah, so I'll tell you what's up. Okay, so here's the question, right? And I think a lot of you guys kind of understood this fundamentally in terms of the tension side. So if you think of, sorry, just getting your attention, please. Okay, so if you think of the bending moment diagram for this beam, right, and you think of it like a continuous beam like this, the bending moment diagram looks like this, right? Where you've got positive and negative bending. Now, the magnitude of these bending moments will actually be able to inform whether your beam is in tension or compression, and by how much. Okay, so the bending moment diagram is strongly linked with the tensile stresses. Okay, so in terms of where to actually draw the Rio, you want to match it up with the bending moments like so. Okay, right. So wherever you've got tension, you draw the reinforcement like so. The one thing you guys missed, all right, is what I was saying with the anchorage. All right, it is better to essentially have these cogs at the ends for tensile anchorage. All right, because it gives you a faster development length and it ensures that your beam will behave as a as essentially like one beam, right, instead of two separate materials. Okay, so that's one. For the second one, okay, so I saw a lot of people do this, which you've kind of got the right idea. So there's tension being developed on the top side, which is true. But again, to get as much of this beam, I guess like anchored as possible together, you would do this, okay? So this basically allows your anchorage, right? If you think of the anchor thing I was talking about, right? So imagine this is like a boat anchor. Okay, oh, I don't know how it's drawn. Anyway, you got your anchor, right? And it's pulling as much of this concrete together as possible during bending like this. Okay, so that's one. But the other thing which I haven't drawn is actually this. Okay, we normally think of a problem as like ending when you see the support, right? But essentially, your bar should start in the wall. Okay, so imagine this is a wall, and then this is like a cantilever beam or slab or whatever coming off of it. You need to essentially have a starter bar in the wall so that it can essentially behave together with the beam. All right, so that actually starts in the wall, is what I'm trying to say. I'll get to the retaining wall last because it's the most complicated. But for this shape, right, very similar to before. So we've got this, except, yeah, like as you guys correctly identified, essentially, you're going to have a switch due to the point loads. But like before, you want these end anchorages as well in tension, okay? And then very similar for this as the cantilever. Okay, so you start a bar into the ground and you've got a cog coming up and grabbing all of the concrete. Okay, so the most complicated one to kind of understand is the retaining wall. Okay, so there's a few things going on, but if you think of the forces, right, and I know not everyone's done geotech, so it's fine, but if you think of soil pressure and earth pressure, there's more and more pressure the deeper you go into the ground, right? So it creates this triangularly distributed load. So that's the horizontal loading. But this is also not immediately obvious, but the base of your footing also behaves as the base of your retaining wall also behaves like a footing. Okay, so all of the weight of this retaining wall is going to actually push onto the soil, right? And that pressure is actually going to push back up, okay? And you'll essentially end up with a relatively difficult deformed shape to comprehend, but just trust me, this is right. And then everything's essentially cantilevering off this point, okay? So what I'm trying to say is on this side is where your tension is being, imagine this is like a sideways cantilever beam, like in scenario E, for the stem of the retaining wall. And like before, you need this to kind of be embedded in the wall, okay? So there's a starter bar. And then it also helps to basically have this cog so that there's a shorter development length there as well. And then for this one, essentially you want to put a bar on the tension side, like so. And I mean, arguably, the tension side flips over to this, but it's such a short, it's called a toe. It's called the toe of the retaining wall. This is such a short toe that it might not be the case. And also you've got this cog almost acting like a pseudo longitudinal bar for the other side. Anyway, that's probably the hardest one to comprehend. Okay. All right. We're going to do a break, but it's going to be a relatively short break because I'm just running out of time for this workshop. So we're going to continue in 3 minutes. So this should give you enough time if you need to go to the bathroom or anything like that. 2 minutes. So you're welcome to promote it as soon as we've done, as soon as the break is over. Sorry, just need to take a little longer. is Sheriff?
So Sheriff is in the
Are you okay with it? Oh shit. No, they just messaged me.
If you don't want to be good,
Do you want to do it? Then you get money.
I didn't read it.
I'm not just say exactly that. Do you want to do it maybe one day, right? You can just, it's okay if we go off I don't know if you want to come back and kind of thing. Look, when they come, I think we'll just cut off.
Actually, I always think that it's been not it's like would you rather like practice stuff?
All right, guys. Sorry. Let's continue. All right. So that's the first questions are that's the first question covered. Now I'd like to switch over to thinking about durability design, right? So remember, durability is to do with protecting the steel. Okay, so there's a few things you need to do. You need to consider essentially like chloride exposure, and you need to consider fire protection. Now, both of these will result in something called minimum cover, and like I briefly alluded to earlier in the workshop, that's to do with how much essentially padding you have around the bar of concrete. Okay, so this is called minimum cover. So some words I want to familiarize you guys with is cover and axis distance. Okay, so cover is the amount of concrete before you reach any steel. Okay, and axis distance is from the edge of the concrete to the middle of the longitudinal reinforcing bar. Okay, so yeah, another one is the fact that we've got this longitudinal bar, or it's sometimes called axial bar. And then you've got transverse bars, right? These stirrups, right? So they hook around the side on the outer edge of the axial reinforcing bars. And when we're talking about cover, we're talking about the distance from the air to the outer edge of that transverse bar before you touch any steel. Okay? Does that make sense? So it's cover. And you can basically work out axis distance relative to cover using geometry. Okay. So, first thing to talk about is exposure classification. So, exposure is essentially it's a combination of a few things. The amount of exposure it might have to sulfates, right, which come from soil, or particular types of soil, moisture, so how wet the surroundings are, and chlorides. Okay, so that's like salt water and things like that. Okay, so just drawing your attention to the left, right, because this is kind of a crowded page, but A1 represents essentially the best conditions, right? So the smallest amount of cover is required in A1 conditions, and then followed by A2, B1, B2, C1, and then C2 is the worst condition, and U is unclassified and refers you to a different standard for like further guidance. So that's like special cases, okay? So C2 is the worst and A1's the best. Okay, so reading this table from AS3600, It tells you a description, a vague description of your type of member and like kind of where it's sitting in the environment. And then it tells you what you would classify it as, okay? So for example, if you've got a member in contact with the ground, here's what I've drawn for your reference. But it's protected by a damp-proof membrane, right? So for example, kind of like, I think it's called poly sheeting. I don't know what type of poly, like a plastic thing, right? If it's protected by a damp-proof membrane, it's got exposure classification A1, and you can just go down the list. In the second categorization, surface of members in interior environments. So if you've got like a beam or whatever you're concerned with, except it's in a warehouse or it's in a whatever, you're following these now, okay? And then the third category is surfaces of members in above ground exterior environments and areas that are, and then it says inland or coastal, okay? So yeah, above ground, but outside basically, right? And then this fourth one is surfaces of members in water, so fresh water or running water, and members which are touching salt water. Okay, so permanently submerged in spray zones or in tidal splash zones. Okay, you know what's kind of interesting? When I was doing research for this, I thought like there was a mistake in the standards or something like this, right? But like I mentioned before, B2 is not as bad as C2, right? But what's interesting is that a member that's permanently submerged is not as bad as a member that's in a splash zone. Okay, so if you think about it, right, we've got a member, and if it's completely underwater, I should probably swap those colors, hey? Fuck. Okay, it's completely in water. It's not actually as bad as if it's kind of in the water and the tide's going up and down. So why do you reckon that is? It's because the process of corrosion essentially relies on oxygen, right? And so if it's starved of oxygen, like when it's permanently submerged, you don't actually have to deal with the same conditions for corrosion as you do if it's constantly getting exposed with oxygen. Do you know what I'm saying? Yeah. But it does have moisture ingress for both cases though. Okay. So climate zones, right? So if you read part 3, where we're talking about members which are outside and above the ground, there's arid, temperate, and tropical climates, right? And so here's a map of Australia that they've got in AS 3600, which is just referring to the different zones, right? So if the question says we're in Charleville, wherever that is, you're in temperate conditions, essentially, right? So you just read off of this map. Okay, there's this table, right? Table 4.4, and this is going to tell you, based on your exposure classification, the minimum strength that's required for your beam or whatever you're pouring, and its curing time, which isn't really a designer consideration so much as it is like a buildability thing, okay? You've got table 4.10.3.2, which tells you the minimum cover. Okay, so you read the exposure classification and you go back to the required strength, right, from the first table, and you match it up and it tells you what your required cover is, okay? And there's also other exposure classifications, which we don't really cover in this course, but this is just from the lecture slides, it's telling you you should also consider these things, okay? Do you guys have any questions about exposure classifications? No? Okay. Next thing's fire protection. Okay, so when there's a fire event, all right, for a beam specifically that we're talking about, it will basically be attacking usually the bottom side of the beam, but sometimes the side as well. And essentially, the rate at which your steel melts versus the rate at which your concrete spalls. So spalling is basically where the non-evaporable water in the concrete dries up, right, due to the flames, and it starts flaking off, right? So your concrete can get damaged in the event of a fire through spalling. Okay, so the rate at which concrete loses strength through spalling is a lot slower than the rate at which the steel melts. Okay, so you want to protect the steel using a cover of concrete of some degree. Except for the protection, for the fire protection part of the code, it doesn't directly tell you what cover you need. It tells you what axis distance you need. Okay, so when I'm talking about axis distance, I'm talking about from the edge of the beam or whatever to the middle of the longitudinal reinforcement, okay? So it will talk to you, it will tell you some kind of axis distance instead of cover, but you can kind of translate one into the other. And I'm going to tell you about a fire resistance period in a second, okay? And you can find the average axis distance using like an averaging formula, basically. Okay, so if you think about, this is essentially like a fire event failure criterion, right? So what the code will tell you is how long your concrete beam, in this case, because we're just going to be talking about it in terms of beams in this course, how long your concrete beam takes before it collapses, okay? And you're going to compare it to something called a fire resistance level, right? And this is from the Australian National Construction Code. And this is to do with how long it takes for someone to escape your building based on its architectural arrangement / functionality and stuff like that, right? So you have to satisfy some kind of fire resistance level, right, which a fire engineer will tell you. For example, it might take 90 minutes to escape this building. It might take 120 minutes to escape this building, whatever. It's measured in minutes, okay? And then as a structural engineer, you use the guidelines in AS3600 to tell you how long your beam takes before it melts, okay, or it collapses, okay? So, here is like tables from the code. So from AS3600, I've shown you two, right? The one on the left is for a simply supported beam, and the one on the right is for a continuous beam, okay? So let's just talk about the simply supported beam first, and this might not immediately make sense what this is referring to, but let me illustrate something for you. So if you've got a beam like so versus a beam like so, okay? If you think about the longitudinal reinforcement, this beam, due to its shape, might have 4 bars, so say 2 top bars and 2 bottom bars. This beam that's a bit wider, the implication is that due to bar spacing requirements and stuff, you're going to basically fill in more bars in the middle, so there'll be more bars essentially on the top row and the bottom row. So this is important because essentially in this table, it's going to be a function of B, which is your width, okay, so the beam width. What we're saying is that if you've got a beam that's skinnier, right, the idea is that you need it to have more cover. I'm going to exaggerate this quite significantly. It's going to need more cover than a beam that is wider, okay, because there's more redundant members, okay, more redundant steel in a wider beam. Okay, so that's what this table is telling you. And this makes more sense when we see it in the example, right? But the idea is they give you a few combinations of what the average axis distance should be when you're considering a certain width for your beam. Okay, and there's different values in this table for continuous beam versus simply supported. So these two images on the left are equivalent. So you can look at it in terms of a table or look at it in terms of a graph. And then also the 2 images on the right are equivalent. So you can look at it in terms of a table or as a graph. Okay, so one more thing I would like to mention is in this course, we only cover fire design for beams, but if you're a structural engineer in industry, you would refer to these clauses for slabs, columns, and walls, which are designed essentially a little bit differently. The main difference I would say is that if you think about a beam, it's essentially like a one-dimensional member, right? Whereas for a slab, it's kind of like 2D, and same with a wall. And the idea with something that's 2D, basically, is that it can actually also act as a fire barrier. Okay, so for example, if there's flames on this side of the wall, it actually insulates whatever's on the other side of the wall. And a similar process happens for columns, right? So the idea with a column, and the wording in the code is for columns used in a firewall, the idea is that, yeah, you've got these columns, but if there's essentially a non-structural wall linking these columns together, it behaves like how you would design a structural wall in terms of the fact that all 3 of these require some consideration for insulation. Yes?
So for this course, do we only deal with the first part of an FRL, the structural part?
FRP, yes. So we calculate just FRP, right?
Which has to always be less than FRL.
Yes. So FRL is always going to be given to you in the question.
Okay, cool.
Just like in the way that if you're a structural engineer, it's always the fire engineer who gives you this number. Like you're not qualified as a structural engineer to like really find this in complicated scenarios, right? Sorry. Okay, let me rephrase that. For very like simple scenarios, I think there is a table that you can refer to. But say you're designing a 30-story building, you need to consult a fire engineer. They'll tell you the FRL. Yeah, but you're able to just calculate the FRP.
Yeah,
every time.
Because FRL has like the three numbers, right? So we only take the first one, like the structural one for beams.
Yes, you're right. Yeah, I know what you're talking about. You've got, let's say, 90/90/90. The first one's the structural integrity one. So for beams, we only consider the structural integrity one. For the others, I believe you consider 2 or 3 of these. So that's referring to insulation and something else to do with integrity. Okay, yeah. Good question. Do you work in industry?
Yeah.
I can tell. Yeah. No, for sure. If you'll see this very, very often in industry. Okay. Any other questions? Okay. Look, before we continue with the second question, I've just got some folks from SevSoc, and they're going to promote an event. All right. So feel free to come up. Feel free to. Do you want to talk into this microphone, or what do you want? It's yeah. If you come up. Talking into the microphone is a lot easier than trying to yell, I guess, to everyone.
Okay, sure. All right,
Yep.
we'll take turns, I guess. All right.
Yep.
Hello, everyone. I'm Sharath, and I'm one of the day coordinators for this year's professional development camp. And so what this is basically is it's just 3 days of us kind of helping you to get the J word, which is of course job. Sorry for saying it, but that's what it is. So we're going to kind of do like resume workshops. We're going to do kind of interview preparation, and more importantly, there's actually leaders from the industry who will come on the camp. So it's like kind of a really good opportunity to actually meet people in the industry because it's very difficult. I mean, like careers fair is like, you know, there's just so many people. It's only like 2 hours. This is like a good 3 days to actually talk with industry and kind of learn things about the industry. Do you want to say something as well?
Yeah. So I know some of you guys are like second year and third year. If you haven't gone there already, I will highly recommend it because it is like your chance to make like long lasting friendship, networking. Come in with your best resume, best cover letter, and we'll check up, we'll fix, and we'll give you like suggestion to fix it. Like for example, me, right, I still keep in touch with people from my time at the camp, including Henry, which is my leader. Yes, I recently like emailed him my resume to like, hey Henry, can you check this for me? And he gave me some really good feedback. So this is like a chance to make a real connection. So I will highly recommend it. Also like cost of food, accommodation and transport is all covered. We just have like, it's not just all like boring things. We'll have party, games, drinks. Yeah, so we'll highly recommend.
Yeah, exactly. Like it's not going to just be pretty much what Maya said. Like there'll also be plenty of fun activities at night. So we're trying to achieve like a good balance where it's like really serious and like you can really kind of learn things that will really help you in terms of landing your internships during the day. But then like drink in the evening, I guess. Do you want to say anything? Oh, do you want to talk about price maybe?
Yeah, so essentially tickets are on sale right now. Early bird tickets have now been snapped up. So we're through the general release now. So tickets are available through our Facebook page and through our Insta bio. How many of us actually applying for internships this year? So many. So this is exactly what you guys would want to come to, especially since there will be, as Sharath and Maya said, plenty of other people that have gone through that same process and can help you at whatever stage you are. So yeah, term 3, week 1. So that's a very good.
Tell them how many slots should we have. We can't take everybody in civil, so I think we only looking at around 120 campus.
It's just there's limited tickets essentially. So be sure to get in quick because we will have a final release as well, which is another bumping price. So just get in while you can.
Get the cheap tickets basically.
Do you want any questions? Over here.
Yeah.
Alright.
Awesome. See you there.
Please come.
Thank you. and I'll be there too, guys. So yeah, that's if you care. All right. Yeah. Anyway, yeah. No, thanks for swinging by.
I'll stay.
Oh, you'll stay?
I'll stay.
Okay, fantastic. All right, let's continue then. All right, sure thing. Stay or leave, up to you. No problems. Okay. All right, let's do a question to do with durability design then. So this question, let's have a read of it. Okay, so this question actually has a part A and part B, which has two different scenarios. So let's do part A first. What is the minimum concrete strength that can be used for a continuous reinforced concrete beam within Sydney Harbour Wharf structure? For this concrete strength, what is the minimum cover needed to the reinforcing steel? Okay, so in the first step, what we do is we identify the exposure class. So just to give you a bit of a recap, where is it? We look at this big table, right? And we want to figure out what subcategory we're dealing with. In this case, we're dealing with case 5, I believe. Yep, so case 5. And essentially, a Sydney Harbour Wharf structure would fall under tidal splash zone. So it's essentially dealing with the worst case scenario, right, which is exposure class C2. So we're dealing with exposure class C2. All right, so now we check this next table, and for exposure class C2, we're told that the minimum concrete strength that we're allowed is 50 MPa concrete, right? So that's step 2 done. Step 3 is figuring out the minimum cover. Okay, so in order to figure out the minimum cover, you need to work out your concrete strength as well as your exposure classification. So basically, step 1 leads into step 2. And step 2 leads in step 3, and you take the information as well from step 1. Okay, so these two are a function. Step 3 is a function of the first 2 steps. So you read this table, all right, like so, and you figure out that the minimum cover is 65 mil. Okay. Am I going too fast? So that's basically it. That's as simple. That's as complicated as it gets, pretty much, when you're figuring out the exposure class and then the amount of cover you need. Okay, so this is a matter of reading the tables and interpreting the language correctly. Okay. All right. Let's look at a slightly more complicated example. So this is part B. What is the minimum strength concrete and cover for a simply supported beam, right, used to support a balcony slab in Bourke, New South Wales, if the beam is 200 millimeters wide, exposed, and required to have 1 hour fire rating? So this is actually, and then this information is not redundant as well. Assume R10 stirrups are used for the shear reinforcement and N24 bars are used for longitudinal reinforcement. So actually, this question is super packed with information. You basically need to consider every single part of the wording of this question. So the first thing is we got to figure out exposure class, just like before. So we're trying to work out the minimum cover required for the exposure class, right? So we're told Bourke, New South Wales. We find that on the map. We figure out that it's a temperate. It's kind of like a temperate classification, right? For our outdoor environment, right? So we're looking at outdoor above ground structures. So the reason why we're choosing above ground is we're told it's a balcony slab. Okay, so because it's a balcony slab, it's not touching the ground. Okay, and then we look over in this row, which says for temperate climate zones, we're choosing exposure class A2. Okay, so that will then lead down the same path as for the previous question. We look at table 4.4, and we figure out for A2 we need a minimum concrete strength of 25 MPa. And then step 3, we locate where 25 MPa is, and we locate where it says exposure classification A2, and we find that the minimum cover that's required is 30 mil. Okay. Yes.
Is that temperate zone part of the Shelley standard?
Yes. So that map. Okay. Basically, I'll show you the whole map again. This is a figure. In fact, you can find it in the standard if you just Control F and then type figure 4.3. It's a map in the standards. However, the standards are black and white. Okay, so you have to read this stupid texture, which is like the line direction, whether the lines are vertical or diagonal or horizontal. So I color coded it because it just makes it easier to look at. All right. But yes, it's in the standards because the standards have to be printable in black and white. Basically, is the short of it. Okay, so that's basically the minimum cover that's required if we were only considering the exposure class, right? Now we have to figure it out for the fire durability design considerations too. So we have to figure out the minimum average axis distance, right? And there's a few bits of information which were in the question which we'll need, okay? So the fact that it was a simply supported beam is actually important information, okay? We're told that we're designing for an FRL. Remember, FRL? Where is it? FRL was the fire resistance level. So this was given to you by a fire engineer already, okay? So you're trying to find something that satisfies it in terms of the fire resistance period. And we're also told that the beam is 200 millimeters wide, okay? So that's dimension is 200 mil. Okay, so I've written here, sorry, I'm gonna delete this real quick so it's clearer. I've written here method 1 or method 2. Okay, so as you can see, you can either use the table on the left or the graph on the right. Either way will get you the correct answer. So let's do it through reading the table first, okay? So if you're looking at this table, you're looking for, you're looking for the row which lines up with the correct FRP. Okay, so FRP being to do with the fire rating in minutes, okay? So we're looking at this row. Okay, combinations, this is kind of like, it's hard to explain exactly what combinations means, right? But you want to figure out which combination best suits what you're trying to look at, okay? So let's do this in purple outline. So we know that our beam is 200 wide, right? So for one of these combinations, it will basically work, and we're looking at this row, right? So in purple, I've highlighted all of the beam widths, right? But specifically, we're looking at this row. So therefore, we're concerned with this is the axis distance, okay? That we're looking for. So I'll show you it from the other perspective, which is if you were to read off the graph instead. In blue, I've highlighted the FRL. Okay, so these lines on this graph represent the FRL or the FRP minimum. And then on this axis is the width, right? So you do the same thing. You're basically inputting the width and the FRP, and as a result, you're looking for the average axis distance, right? But in both cases, you get the number 30, right? So you can use either method and it'll get you the same thing. So we're told that the axis distance is 30 mil. Now we have to consider the other information that was given in the question, and that's the bars basically, right? So we're told that the axial bars were N24s, right? And the transverse bars or the stirrups, right? So transverse bars being these ones. These ones. Okay. And then axial bars being these ones, like so. Okay. So the bar diameter, right, for an axial bar of N24 is 24. And the bar diameter for an R10 is 10. Okay. But you can think of it like this or just plug it straight into the equation. But the idea is we're trying to solve for the cover, and we know this dimension. We know AS. So do AS, subtract the stirrup, right? So we're doing this whole thing. We're subtracting the stirrup, and then we're subtracting half of the diameter of the axial bar, and that gives us the remainder being just the cover. Okay, so that's what we're ultimately solving for. And the cover, I believe, is 8 mil, but let me just double check. 8 mil. Okay, so the minimum cover is the max required, right, which might not makes sense immediately. The max required by exposure classification and fire protection, right? So we found in the very first part, exposure gave us that the minimum cover was 30, and for fire protection, the minimum cover was only 8 mil. Okay, so the max between the two is 30, which is now the minimum cover. Okay, so why does that logic make sense? Think about it like this, right? There's a nightclub, okay? There's a nightclub, there's a bouncer, and this nightclub is only for highly influential people, okay? So the bouncer tells you to get into the door, you need to fulfill 1 or 2 criteria. The first one is have 1 million subscribers on YouTube, okay? And the second one is have $1 million minimum, okay? So the idea is you need to fulfill at least one of these requirements to get in the door, okay? And if you had only, let's say, $1, right? But 1 million subscribers, essentially, okay, my analogy is breaking down, but if you think about it, right, this logic makes sense, all right? Okay, yeah, keep talking, Henry. All right, so let's move on. Let's talk about the last thing I want to talk about today, load combinations, okay? So there's actually a lot to cover, and I wonder how much of it I'll actually get through today. Otherwise, I'll cover it next week. But the idea is that we're going to be talking about load combinations and statics, and the statics part will be kind of a revision that you'll see in the question. But the load combinations may or may not be new to you depending on whether you've done steel structures or not, okay? Okay. So in order to basically make sure that a building doesn't fall down, all right, let's say we've got that scaffolding example again, right? So we've got 3 dudes on a scaffold, right? The loads are the dudes, right? So, and how strong that structure is the capacity. So we want to make sure that the capacity is able to take on more than our loads, which are the dudes, all right? So there's 3 standards which are involved in this process, right? And the one that we will be talking about today is the load combinations, right? So we're specifically talking about the left-hand side of this equation, aka how much you need to consider increasing the weights of these dudes, for example. So if they're 100 kilograms, let's say we need some kind of dynamic load factor in case they jump or something, you might want to scale it up or something like that, okay? So that's basically what load combinations means. How much do you scale it up by? Okay, you've got different types of loading. You've got dead loads, you've got live loads, and you've got other loads which aren't in this course, like wind loads and earthquakes and things like that. So let's just talk about dead and live loads for now. Dead loads can be split up a bit further into self-weights and superimposed dead loads, okay? So if you imagine, let's just say we're talking about a concrete slab. For example, we're on a concrete slab right now. The floor is a concrete slab. This slab is relatively heavy. So unlike steel, right, unlike steel structures, the course, right, we actually need to consider the self-weight of this concrete slab. In real steel design, you do need to consider the self-weight of steel as well. But in the course that you may or may not have done in Term 1, you don't actually consider the self-weight of the steel because it's so much stronger than what it can, than how much it weighs, okay? For concrete, these numbers are actually relatively similar to each other. How strong the concrete is relative to its weight. So we definitely need to consider the self-weight of the concrete, okay? So concrete's unit weight, which means how heavy it is in kilonewtons per meter cubed, is 24 to 25 in this ballpark. It'll always tell you in the question. For superimposed dead loads, imagine you've got this floor slab and we've got things we can't move. Like, for example, let's pretend this lectern. There's no way you can remove it, okay? So that would be a superimposed dead load. It's going to be here for the entire duration of the building and until it's demolished or whatever, right? So that's a superimposed dead load. What is a live load? A live load might be me behind the lectern and it might be you guys in your seats, okay? These are loads which on one day it could be there, on a different day it could not be there, okay? So that's the idea of a live load. Okay, so why do we need to consider these loads differently? And it's due to the idea of load combinations, right? You have two different load combinations you need to consider in this course, 1.35G and 1.2G plus 1.5Q, okay? So the top one is considering just the dead loads only, and it's where you scale the dead loads up by 35%. Whereas for the bottom load case, you scale up the dead loads by 20%, and then you add on the live loads and scale up the live loads by 50%. Okay, so mathematically, this will make more sense when we see a question. Okay, so I've only got 10 minutes left, and I think the other class, they're lining up now. So we will try to finish this question in time. Whether we'll actually get there or not, it's questionable. But let's see how far we get, and if I don't finish it, we'll finish it next lesson, all right? So the question says, determine the factored bending moment, M star, for the simply supported member, as you can see on the right-hand side. So this doesn't look too different to what you've probably seen already in 1300. The only thing now is that instead of giving you absolute loads, like 10 kilonewtons or whatever, they tell you it in terms of dead loads and live loads, okay? Right. So we're told that there's a dead load uniformly acting on the beam of 5 kilonewtons per meter, and also a live load, which is acting uniformly on the beam of 4 kilonewtons per meter. And there's also a dead load of 45 kilonewtons from a brick wall as a point load in the middle of this beam, okay? So we're basically told, essentially, the SDL is 5 kilonewtons per meter, right? Which is the uniformly distributed load due to the dead loads. 1 second. Okay. However, we're not told what the self-weight is, okay? So I'll tell you how to calculate the self-weight. So we're told in the question, take the density of concrete as 24 kilonewtons per meter cubed, right? In other words, we're going to substitute in 24 kilonewtons per meter cubed. The next thing we need to do is calculate the area of concrete that we're going to multiply this by in order to get a kilonewton per meter load. The idea is, if you think of a concrete beam, and I'm going to draw the beam as per the description, right? Or roughly, okay? So we've got a depth of 600 mil, and we've got a width of 400 mil, right? So the idea is, okay, if I draw like kind of the 3D-ness of the beam, we're going to multiply the density by the cross-sectional area of the beam, okay? And that's going to give us the uniform distributed load per meter, okay, along the beam. All right, that's what we want to do. So we want that cross-section, right? Except instead of in millimeters, we're going to do it in terms of meters, okay? Because our units in this particular equation is already in meters. So we're going to do 0.6 meters multiplied by 0.4 meters, right? Which is going to give us the cross-sectional area in meters squared. Okay, and then this will give us a uniformly distributed load of dead load of 5.76 kilonewtons per meter. Now, as I mentioned before, the dead load is equal to the SDL added onto the self-weight. So we can actually just add these two things together and we get 10.76 kilonewtons per meter. And then we were already told in the question that the live load was 4 kilonewtons per meter. And we were already told that that point load due to the brick wall was 75 kilonewtons, okay? So when we're considering the free body diagram of our load combination 1.35G, we actually completely ignore the live loading, okay? And what we do is we just consider the dead loads and we multiply it by 1.35 kilonewtons. Sorry, 1.35. We just scale it up by 35% rather. Okay, so that gives us these numbers, all right? Yeah, does that make sense? All right, and to be honest, we're running out of time. That is the free body diagram. And not to cop out or anything, but I think you can figure out the bending moment diagram by yourself. I'll also show you the numbers in a second. But that's one loading scenario basically, right? That's the new part, right? This stuff is all to do with 1300. The second scenario is a free body diagram of 1.2G plus 1.5Q, right? So what we're doing is we're only considering the dead load, point load, and scaling up by 20% for this point load, right? So this point load becomes 90 kilonewtons, okay? However, the uniformly distributed load, we can actually factor and add together, okay? So this uniformly distributed load becomes 18.912. And then you conduct your analysis using these two numbers, 90 and 18.912, instead of 101.25 and 14.526. And so what you'll end up with is two different maximum bending moments, and you compare which one's bigger, right? In this case, it's where you're considering the load combination of 1.2G and 1.5Q, and that will give you the larger bending moment, right? Which is in the middle of the beam. Does that make sense? Okay, what I'm gonna do is, that's the end of the class, so I'll stop recording. But I'll also just